4.3, the fundamental theorem of calculus. We're going to start with introducing an evaluation theorem. So if f is continuous on AB, then integral from a to b f of x dx is capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, big F prime is equal to little f. Example, if f of x is x squared, we want to evaluate definite integral from 0 to 1 f of x dx. That is integral from 0 to 1 x squared dx. So that is equal to, according to our evaluation theorem, big F of 1 minus big F of 0. And we know what the antiderivative of x squared is. That's x to the third over 3. Okay, so that is equal to 1/3. If you plug in 1 for x, it will be 1/3 minus 1/3 times 0, right? 1/3, 1 to the third. So that's equal to 1/3. Okay. Another example. Find the area under the cosine curve from 0 to b. Where b is between 0 and pi over 2. So our function f of x is cosine x. The antiderivative big F of x is, of course, sine of x, because the derivative of sine is cosine x. We already learned about antiderivatives in chapter 3. So to find the area under the cosine curve from a to b, in this case from 0 to b, that is definite integral from 0 to b cosine x dx, which is, according to our evaluation theorem, that is big F, any antiderivative of little f, so sine of x. And we evaluate it by writing a vertical line from 0 to b. So that is sine of b minus sine of 0, but we know sine of 0 is 0. So that area is equal to sine of b. So in particular, if b is equal to pi over 2, we're talking about the area under the cosine curve from 0 to pi over 2. So this is 1, and this is the cosine curve. We're talking about this area. So if b equals pi over 2, the area of this region would equal to definite integral from 0 to pi over 2 cosine x dx is equal to, we had sine of b, but b is pi over 2, so sine of pi over 2, which is 1. So we just found that this area is equal to exactly 1. Another example with the evaluation theorem, evaluate definite integral from -2 to 1 x to the third. So find the antiderivative of x to the third, and that is x to the fourth over 4. Evaluate from -2 to 1. So first evaluate the upper bound, so that's 1/4 minus, evaluate the lower bound, negative 2 to the 4, that's 16 over 4, so negative 15 over 4. Another example. This time we have a question. What is wrong with the following? Calculations. So I have integral from negative 1 to 3, 1 over x squared dx, and we're proceeding with, let's write this 1 over x squared as x to the negative 2, negative 1 to 3 dx, so antiderivative, you add 1, so x to the negative 1 over negative 1, evaluate from negative 1 to 3, and you get negative 4/3. So something is wrong with this calculation. We'll see that we have a problem because, first of all, we got a negative area, and if you graph a function f of x equals 1 over x squared, we see it's positive everywhere for every x. So from negative 1 to 3, we're talking about this area. And that should be positive. And we got negative 4/3. So the problem is our function is not continuous at x equals 0, right? So we have f of x equals 1 over x squared is discontinuous. We have infinite discontinuity at x equals 0, so we cannot apply our theorem because evaluation theorem applies only to continuous functions. On the interval from a to b. Okay, so the calculations are wrong because we couldn't apply the evaluation theorem in the interval from negative 1 to 3 because 0 is in there. So we say this integral from negative 1 to 3, 1 over x squared dx does not exist. Okay, so the fundamental theorem of calculus, which we're gonna do next, establishes the connection between differential and integral calculus. So I'll abbreviate this. Fundamental theorem of calculus establishes the connection between differential and integral calculus. So we remember in differential calculus, the essential problem was the tangent problem. In integral calculus, we have the area problem. So if we look at a function g of x that is integral from a to x, f of t dt, you notice the lower bound a is fixed, but the upper bound, it's a variable. So a picture that can illustrate this. This is our function y equals f of t from a fixed point a to, this is b. However, our x is between a and b. So f is continuous function and x is between a and b. So we're talking about the area under the curve from a to x. And this is changing as x is changing and moving from a to b, then this area, which we named the g of x, is also changing. So we're ready to introduce the fundamental theorem of calculus part 1. So we'll break it down in 2 parts. Fundamental theorem of calculus part 1. If f is continuous on some interval from a to b, then the function g defined as integral from a to x f of t dt, where x is between a and b, is an antiderivative of little f. That is g prime of x is equal to f of x. And here x is between a and b. So example, to clarify this, find the derivative of g, where g is integral from a to x square root of 1 plus t squared dt. So we notice we don't have to integrate here. We don't have to find what g of x is. We need to find g prime of x. So first, what is our f of t? Our integrand, f of t, is square root of 1 plus t squared. It's continuous. So by the fundamental theorem of calculus, part 1, we have g prime of x is equal to our function f of x, square root of 1 plus x squared. All right, so after you determine f of t, all you have to do is put x for t, and that is your g prime of x. All right, another example. Find d dx of integral 1 from 1 to x to the 4th secant t dt. So we have to be careful using the chain rule here. So be careful using the chain rule here and the fundamental theorem of calculus part 1 at the same time. So the problem is we have x to the 4th, not just x, but a function of x. So what we need to do is a substitution. Let u equals x to the 4th. Then we're going to use that d dx is the same as d du times du dx. Okay, so now we're continuing a problem here, equals, instead of d dx, I'm going to do d du, and then the integral with the substitution from 1 to u, secant t dt, and then du dx. So I'm separating it. So everything in terms of u is here on the left side, and according to the fundamental theorem of calculus part 1, the du of this integral is exactly secant of u. And now I have times du dx, and du dx is 4x to the 3rd. And finally, u was x to the 4th, so I have 4x to the 3rd, I'm going to put on the front, and then secant of, instead of u, I'm going to put x to the 4th. And that's it. So we're ready to introduce the second part of the fundamental theorem of calculus, part 2. And that is our evaluation theorem. So we already know that. If f is continuous on an interval from a to b, then integral from a to b f of x dx is equal to capital F of b minus capital F of A, where capital F is any antiderivative of little f. That is, the derivative of big F is equal to little f. So example, integral from 1 to 9, square root of x dx is equal to integral from 1 to 9. Let's write down square root of x as x to the 1/2 dx. And that's equal to any antiderivative of x to the 1/2 would be x to the 3/2 divided by 3/2. Evaluate this from 1 to 9. And after your calculations, you should get 52/3. So differentiation and integration are inverse processes. And a fundamental theorem of calculus bring these two together. All right, so let's state the fundamental theorem of calculus with both parts one more time. So fundamental theorem of calculus, suppose f is continuous on AB. Number one, if g of x is equal to integral from a to x f of t dt, then the derivative of g prime of x is exactly the integrand f of x. And number two, integral from a to b f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime is equal to little f. And that is the end of this part 1 video. I'll have part 2 with mainly examples illustrating both parts of the fundamental theorem of calculus.